Here's another Newton's second law walkthrough. Take a look at the setup here. You've got a frictionless plane with an angle on there of 30 degrees, and it's connected. There's a connection of a cord of negligible mass between the two masses. The one on the left is 3 kilograms. The one on the right is, that given to us, is 1 kilogram. You've got a force of 2.3 newtons pushing on the larger mass to help it accelerate to the right, and this one obviously has some of gravity pulling it in that direction. And our goal is to figure out what is the tension in the connecting cord, and then we're going to try to figure out what's the largest value of force that pushing force can have without the cord becoming slack, which means zero tension. Okay. Well, it's always good practice to set up with a free body diagram what's going on. So if we look at mass 1, that is 3 kilograms, and we're going to have two forces going to the right. We're going to have the force of whatever that push is, just 2.3 newtons to start, and then we're going to have our tension force, which I'll call T. We're, of course, going to have mg and our normal force, which will be equal in magnitude right now, and we don't have to stress too much about those because there's no friction involved. So that's mass 1 free body diagram. Let's take a look at mass 2 free body diagram. So M2 is, I'm going to call that my x-axis now. There's my y. Got my maps right there in the middle. See if I can color that in without it deleting. We've got a normal force. We've got a force of gravity. And we've got some of that pointed parallel to the slope. And that's going to be mg sine theta, and we have some of that pointed directly into the surface, which we'll call mg cosine theta, and slowing it down will be whatever that tension force is pointing backwards. There we go, it's better looking. So we'll have a tension force pointing backwards. Now we know there's going to be an acceleration for the block on top to the right, and we know there's going to be acceleration of this block that's on the ramp. And remember, all this pulley does is it just changes the direction. It's an ideal pulley and it's an ideal rope, so it's not going to affect the overall force, and the tension is going to be the same at all points throughout that wire. So what's the tension at the beginning? Let's set that up. Let's get our Newton's second law equations. Now the first one, I have that the force of the pull plus the tension force is going to equal mass 1 times the acceleration. And in the second instance, I have the tension force is working against the direction of the acceleration plus mg sine theta, and that'll tell me how much mass 2 is accelerating. Well, let's add these equations together. The internal forces will cancel out, so I end up having 2.3 newtons plus 9.8 sine, and what's my angle for this? Sine 30 newtons equals m1 plus m2. So I'll figure out my acceleration. That's 4 kilograms over there. That's 4.9 newtons plus 2.3 newtons. And I get 6, 7.2. So I get 7.2 newtons divided by the 4 kilograms will equal my acceleration. So I get an acceleration of 1.8 meters per second squared. Okay, great. Now I know my system's accelerating, so I can plug back in and figure out what the tension force is, because the tension force has to be enough to help this one get up to that acceleration and to slow this one down so it gets that acceleration, because without that acceleration, it would have the 4.9 meters per second squared acceleration, since that's the proportion of gravity that's acting on block 2. So if I cut that cable, this one would immediately begin accelerating at 4.9 meters per second squared, given that it's frictionless. Anyway, let's backfill in. Pick your equation that you like. So we'll do 2.3 newtons plus the tension force equals the mass of the first one and the acceleration. And we end up getting the tension force in the first case should be 3.1 newtons. Okay, you can check the other equation to make sure it works for both, because it should be the same, given the ideal. All right, what's the largest value of the magnitude force may have without the cord becoming slack? Well, in the second case, we want the tension to be equal to 0. So that's what we want. That's our critical value. If the tension equals 0, the cord will be slack. So if we take our equation and we figure out, for either one, we set the tension equal to 0. We can do that with the second one. I mentioned it previously, but if we take our equation for Newton's second for block 2, and we solve, setting t to 0, what we end up getting, our masses will cancel off, and we get that the acceleration has to be gravity times the sine of the angle. So our acceleration has to be 4.9 meters per second squared. What does that mean? That means this thing is accelerating at the same speed this would be accelerating in order for it to have 0 tension. Similarly, if they were falling in free fall, if they were following each other vertically, if both were in free fall, they'd have the same acceleration. There would be 0 tension in the cable or the rope. Okay, so if that's our acceleration, then we just need to figure out what does that force have to be plus that 0 tension in order to equal that desired acceleration of 4.9 meters per second squared. And we'll end up getting, we know the mass there is the 3 kilograms times the 4.9. Okay, so we get the force of the pull has to be, force of the push has to be 14.7 newtons. And with that amount of push, you should have 0 tension in that line. I hope you found this video helpful.